In the previous videos, we looked at how to assess available data, establish a baseline, and understand the savings mechanism associated with your pumps and fans energy savings projects. Now, you'll apply this knowledge to select a savings calculation methodology that's appropriate for your system and doesn't result in estimates that don't reflect reality. Remember that there are three main mechanisms to achieve energy savings: reducing flow, reducing pressure, and increasing efficiency. Let's look at an example of flow reduction. This project involves a thermal heating loop with a dedicated pump controlled by a three-way valve that provides heat to an industrial press. The project will install a VFD to replace the function of the three-way valve, controlling the pump speed to meet the heating demand and eliminating the recirculation of excess fluid. Let's start by assessing the data available to develop the baseline and estimate the savings. While we only have a few amp measurements for the pump and motor nameplate data, we know that the pumps are running continuously. Although the valve positions vary, the three-way valve means that the pump flow and therefore the motor load are relatively constant. We can therefore expect to develop a reasonably accurate baseline from the spot amp measurements. Checking the motor nameplate data, we see that the amperage measurements are 75% of the rated full load amps. We can use the nameplate voltage and power factor to estimate the baseline power without any adjustments. There are no logged data for the pump motor, but we can develop an accurate estimate of annual runtime from operational data, including 12 months of valve positions, oil temperatures, and press speed. Having assessed what data are available, we can then calculate the annual baseline energy consumption. The project baseline is the sum of the power of the 5 pumps multiplied by the annual operating hours. With the baseline established, we can turn our attention to understanding the savings mechanism. This is a flow reduction project that eliminates the excess flow within the bypass loop. Calculating the future flow requirement from the process heat load using first principles or other methods would help, but it doesn't give us the full picture because we don't know the current flow rate. A simpler approach is to use the valve position data mentioned above as an indicator of the percentage of current flow required by the process. For example, if the valve position is 55% open, this indicates that the flow can be reduced by 45%. We can then use the affinity laws to estimate the post-project power from the percentage flow reduction. If pump and system curves are available, it would be good to check them to see how this reduced flow would impact system operation and pump efficiency. Without these data, we can make a quick assessment of whether just using the affinity law alone gives an accurate estimate. In this case, there's no significant vertical lift in the system, as it is a loop, so we can assume no static head. However, we are dealing with a reduction in pump speed of more than 20%, so there is a risk that the affinity law overestimates the savings. Next, let's look at an example of pressure reduction. This project involves several fans recirculating hot air within a drying process. The project involves the installation of VFDs and fan re-sheathing to replace the function of the iris dampers currently used to achieve the desired airflow rate. This eliminates the pressure drop across the dampers. Again, we start by assessing the data available to develop the baseline and estimate the savings. We only have a few amp measurements for each fan, plus motor nameplate data, but we know that the damper positions are manually controlled and rarely changed. Therefore, we can be reasonably confident that the motor loads are relatively constant and can expect to develop a fairly accurate baseline from the spot amp measurements. Checking the motor nameplate data, we see that the amperage measurements are 75% of the rated full load amps or higher. We can use the nameplate voltage and power factor to estimate the baseline power without any adjustments. There are no logged data for the fan motors, but we can develop an accurate estimate of the annual runtime from 12 months of dryer operating data and discussions with operators about standard procedures for turning the fans off when the drying process is shut down. In this case, 2-speed motors are used to drive the fan. The low-speed setting is only used when the dryer is warming up. It's ignored in this analysis as these savings are expected to be negligible. Having assessed what data are available, we can then calculate the annual baseline energy consumption. The project baseline is the sum of fan power multiplied by the annual operating hours. With the baseline established, we turn our attention to understanding the savings mechanism. This is a pressure reduction project. In the base case, the outlet dampers impose a frictional resistance to achieve the desired airflow, but create a pressure drop in the process. The project will reduce fan speed via VFD or resheathing to produce the desired flow at the minimum required pressure. If we had baseline airflow measurements and fan curves, we could estimate the ideal brake horsepower requirements by plotting the airflow on the curves, or we could do a first principle calculation by making a reasonable assumption about the fan efficiency. In either calculation, the brake power must be multiplied by the motor and VFD efficiency to obtain the input power. Unfortunately, in this case, we're unable to take baseline flow measurements because there's no access to a suitable measurement location. However, we have damper positions that we can use to estimate the friction losses in the system. If we had the damper characteristic curves, we could interpolate the pressure drop directly from the damper position. Without these, our best option is to estimate the flow reduction introduced by the damper and use the affinity laws to calculate the post-project power. Similar to the previous example, we can use the affinity laws with some confidence because the fans are recirculating air, so the static head or lift should be minimal. In the absence of measurement, always be conservative when estimating flow reduction from dampers to avoid overestimating savings. The relationship between damper position and flow is rarely linear. For example, a 50% open damper often results in airflows greater than 80% of full flow with the damper wide open. The affinity law calculation is similar to the previous flow reduction example, but in this case, we use the rated fan power instead of the baseline power because we need an estimate of the hypothetical power at full flow. As with the previous example, we should ask ourselves whether the savings are too optimistic. With a 25% speed reduction, it may be reasonable to assume some reduction in fan efficiency. Alternatively, you can apply a modified exponent to the affinity law calculation. This is not scientific, but it may be prudent. Regardless of which calculation method you use, it's important to be aware of its limitations. Common calculation mistakes that lead to inaccurate savings estimates include overestimating flow or pressure reductions, overestimating the baseline power. Throttling valves and dampers are not the most efficient controls, but they do reduce load compared to full rated power. Failure to verify reasonableness of estimated savings against total baseline consumption. By using this structure to estimate savings, you can be confident that your savings estimates are grounded in reality.